Hi everyone, I'm Manasij. This talk is about speeding up superoptimization with data flow analysis. This is joint work with Pranav, Zhengyang, and John from the University of Utah. I'm going to start with some background describing superoptimization and program synthesis, then the motivation for our work, then our solution which utilizes data flow analysis, and finally some of our results where we show a performance improvement in our open source superoptimizer named Super. The context of this work comes from optimizing compilers. Modern compilers have a large list of inbuilt people optimizations. These optimizations are applied to any code the compiler encounters. Now, this is a one-size-fits-all approach, which is a compromise between effectiveness and the engineering effort required to maintain a compiler. Superoptimization, on the other hand, is an alternative to this approach, where the goal is to generate optimal code. Now, Super tries to do this by synthesizing optimizations tailored to the code being compiled. Now, given a source pattern, Super comes up with a replacement which is better according to some cost model. For example, a shift might be significantly faster than a multiply on an embedded processor. Also, for the optimization to be sound, the replacement has to refine the source, which means it has to produce the same result in the absence of undefined behavior for all possible inputs. For convenience, I'm going to refer to the stronger property, which is equivalence, for the rest of this talk. Now, Super synthesizes these optimizations by enumerating a large number of candidate solutions. This method is known as enumerative program synthesis. Super's approach to enumeration is lazy, which means that the candidates can have holes and symbolic constants. The enumeration starts with a hole, indicated by an H here. Holes get expanded recursively into other candidates until a certain depth is reached. Another possibility for a symbolic candidate is a symbolic constant, indicated by a C here. Now, this is lazy because we do not have separate candidates for each concrete constant like 0, 1, 2, 3, and so on. Instead, Super attempts to synthesize a concrete constant with the CG loop. Now, this enumeration process can quickly result in a very large number of candidates if we are not careful. And that brings us to the motivation of this work. The search space for the enumeration is too large, and we want to reduce that. The search space is large because each hole can expand into a bunch of expressions which can contain holes themselves. Another bottleneck for enumerative synthesis is how rapidly it's possible to discard infeasible candidates. This equivalence check is typically done with a SAT or SMT solver. This can be slow sometimes. For example, the solver queries used to synthesize constants involve alternating quantifiers or a CG slope, which can be very slow. Now, to summarize, one bottleneck for enumerative synthesis is a large search space, and the other one is slow verification. A larger search space means more solver calls, which sort of compounds the performance problems if the solver calls are themselves slow. So we somehow have to prune this search space and not follow branches which do not lead to feasible solutions. This brings us to the main topic of this talk, which is pruning the large search space. Our enumerative synthesis approach has both concrete and partially symbolic candidates, those with holes and symbolic constants. The pruning problem boils down to asking an inequivalence checking problem, which is given a concrete specification and a partially symbolic candidate, can we prove that the candidate is infeasible? That is, are all the expansions of a candidate infeasible? And we have to solve this problem without enumerating all the expansions of a symbolic candidate. Otherwise, we might as well use a solver to check this. So how do we do that? Let's look at a simpler equivalence checking problem first, which is equivalence checking for concrete candidates. We have a specification x squared plus 1 and a candidate which is just x. Now, showing that x is inequivalent to x squared plus 1 does not require a solver. We can just choose an input, which is, for example, 2. And if the outputs are different for any input, we can conclude that the candidate is inequivalent to the specification. However, let's try to figure out if this approach works for partially symbolic candidates. For example, if our candidate was x plus c. Now here, we can evaluate x squared plus 1 like before, but because c, a symbolic constant, cannot be evaluated, the exact same approach cannot be useful. Now, this work is about an analogous approach, which is the symbolic candidates can be abstractly interpreted instead of being evaluated. Now, as concrete evaluation produces a concrete result, abstract interpretation produces an abstract result. For example, a range of integers might be an abstract result. It's possible to, for example, analyze a function and show that the result is always between 5 and 10, regardless of what the input is. So how does this solve our problem? Here is an example. The specification here is x squared or 1. Now OR is bitwise OR here. And the candidate is very symbolic. It's the whole left shifted by a symbolic constant. Notice that the specification always produces an odd result because the least significant bit is 1. And we can show that the candidate always produces an even result. This is because whenever possible, Super avoids synthesizing no op. And C being 0, that's the left shift by 0 is a no op. Now taking that into account, C should be at least 1. That means that the result is even. So we have a specification which is odd, and we have a candidate which always produces an even output. Now clearly this cannot be equivalent. Let me explain how this analysis works in a bit more detail. We use an abstract domain called known bits. Known bits analysis tracks individual bits of values and tries to prove them to be 0 or 1. There is a third option, which is unknown, which is when known bits cannot conclude anything about a particular output bit. Now this is the same example as before. So the way known bits handles this analysis is it would show that the least significant bit of the specification is 1 and the least significant bit of the candidate is 0. And all the remaining bits are top or unknown. This is a sufficient condition to show that the candidate is infeasible without enumerating all the instructions which can result from the whole or all the constants which can result from the symbolic constant. However, this method of analyzing both the specification and the candidate is not very precise and does not always work. To find a solution for this, let's revisit the equivalence checking problem for concrete candidates again. So we have a specification and a concrete candidate, which is x squared plus 1 and x. We choose an input and show that the results are different. Now this step of choosing an input can also work with abstract interpretation. And then the abstract results are indeed much more precise when it can assume an input value. The way it would work with known bits analysis is, suppose we have a candidate x and h. Recall that x is a whole here. If we choose x to be 0, all the bits of x and h are concluded to be 0 according to the transfer function on the right here. Now we can use this result to show the candidate x and h is inequivalent to a specification, say x squared plus 1. Now choosing x to be 0, the specification can be evaluated concretely to the value 1. Now the known bits analysis concludes that all the bits of the candidate are known to be 0. Hence, all bits of the expansions, all bits of all the expansions of x and h are 0. This means we can skip enumerating x and h and prove that this cannot produce a feasible solution. So we have 5 abstract domains. 3 of them require forward analysis, and the last 2 required backward analysis. I've already described known bits here. For the rest of this talk, I'll describe ranges, bivalent bits, and force bits. Our ranges abstract domain encodes a range of integers. Now these ranges can be wrapped because we are working with bit vectors. The semantics of this range domain matches the one used in the LLVM compiler infrastructure. The way pruning works with ranges is analogous to known bits. We choose an input, evaluate the specification to a concrete value, then we analyze the candidate taking into account this input assumption. This produces a range. Now, if the value from the specification is not in this range, we can show that this candidate cannot produce a feasible solution, and we can show this without having to enumerate this symbolic candidate. Another analysis we have is the bivalent bits analysis. This is also a forward analysis. An output bit is bivalent if it's possible to find 2 inputs such that the value of the output bits is different for these 2 inputs. So in the absence of symbolic constants, this analysis is a dual of the known bits analysis. That is all known bits are not bivalent. However, symbolic constants make a difference here. According to known bits, a symbolic constant is completely unknown. But here, a symbolic constant is explicitly non-bivalent. And this distinction makes it possible to use this analysis to prune candidates which cannot be pruned by the known bits analysis. For example, consider the specification x squared or 1 and the candidate x plus c. Here, the least significant bit of the specification is known to be 1, same as before. Now, the least significant bit of the candidate is bivalent. That is, regardless of what C can expand to, we can show that there are two inputs which produce distinct results in the least significant bit. And that alone is sufficient to show that this candidate cannot produce a concrete candidate which is equivalent to the specification. The next abstract domain, which is the last one for this talk, is force bits. This is a backwards analysis which finds out which values or bits of a symbolic constants are forced to a particular value. For example, choosing 3 as the input here forces the symbolic constant C to be 7. That is, 7 is the only possible value of C for which this specification and this candidate is equivalent when x is 3. Now let's choose a different x, which is 1. Now the specification evaluates to 2, which means C is now forced to be 1. Notice that the first input forces C to be 7 and the second input forces C to be 1. This means there is no C which works for all inputs. And by definition, a symbolic constant has to expand to a concrete constant which works for all inputs for this to be a feasible candidate. So we can discard this candidate without any kind of enumeration or solver calls. I'll now briefly describe our result. The techniques I described in this talk speeds up Super by more than a factor of 2. We measured this by having Super synthesize optimizations for the SPEC CPU 2017 benchmarks, which consists of C and C++ programs. And this was measured with a 128 thread machine with a individual problem timeout set to 300 seconds. This scatter plot shows that pruning solves a problem much faster more often than not. The x-axis is the time taken to solve a problem without pruning, and the y-axis is the time taken with pruning. Now this time allotted for each problem is limited to 300 seconds. In this picture, everything below the diagonal here indicates a pruning win. Now another consequence of this technique is that we can synthesize 8% more optimizations with Super. Now this is because the number of problems which used to take more than 300 seconds and hence timed out are reduced by 40%. And that makes this nice difference where we increase the capabilities of Super with this nice pruning technique. This brings us to the end of this talk. Thank you for listening, and please reach out to us if you have questions. Thank you.